Hi, my name is Abdulaziz Al-Jaber. I am part of a Capstone group that oversees designing a concrete breaker. Our concrete breaker is suited for the average homeowner. The days of being intimidated by using a jackhammer, hiring a professional that costs a week paycheck, or tweaking your shoulder by using a sledgehammer to break some concrete around your house are gone. We have built our concrete breaker to be user-friendly, safe to use, and cost-efficient. Now allow me to introduce the rest of the team. Abdurrahman Al-Balharith, Elisa Velez Acosta, Fadi Shaheen, Kush Patel, and Michael Ilyasi.
There are 3 reasons of why we should care to design a new concrete breaker. The normal concrete breaker that is in the stores now costs a lot of money to own one of them. Also, you need to be professional in using the concrete breaker so you do not get injured. With the current available technology, people who are older or may have disabilities are not be able to cheaply break their own concrete. Thus, a new concrete breaker design that is easy to move and more affordable than the commercially available design need to be created to meet customer needs. The most important customer needs are affordable, break 4 inches of concrete, safe to use, under 1 minute cycle operation, easy to assemble, disassemble, and move. Thus, the group came up with a design to meet those customer needs to make it affordable for most people to buy and simple enough for most people.
This is our customer requirement versus engineering requirement matrix. The requirements that Abdul Rahman previously mentioned have driven the engineering requirements that we deemed essential to bring the customer's idea to reality. In order for the concrete breaker to be portable, we have kept the design simple as to be quickly assembled by the user. Our design is able to break 4-inch slabs of concrete, and to do so, the H-breaker has been built with an optimized hammer and sturdy frame.
Three main challenges we have faced are redesigning our project, staying below a $100 budget, and staying below a 50-pound weight limit. During the team's first meeting with the sponsor in fall, the sponsor had mentioned that he wanted an automated concrete breaker that can be controlled remotely. Specifically, press a button, then go have coffee while the breaker does its job. He then mentions to keep the design below $100 and weigh no more than 50 pounds. The team brainstormed on how to make an automated concrete breaker that is cheap and light, without using hydraulics or pneumatic functions. The team concluded that our motor will be necessary. They designed 8 prototypes but felt confident about one. They met with their sponsor after 6 months of research. Unfortunately, the sponsor discarded all of them but one. His reasons were that the designs were complicated and may cost too much to manufacture. They reworked the prototype in the last 3 months with updated requirements that exclude a remotely controlled feature. Even though the current design was approved by the sponsor, it was above budget by 50% and weighs about 100% more than the sponsor's requirement.
These are the customer requirements and initial ideas that were given to us by our sponsor. We did a lot of research and brainstorming, and we came up with multiple design concepts, and they are: rotary inspired mechanical concrete breaker, pulley with clutch engagement, tensile impact. All of these 3 designs were refined using the sponsor's first customer requirements and needs. These designs were inspired by different mechanisms that were found after doing a lot of research. The focus of these 3 concepts was automating the process and achieving high impact, which were the most important requirements for the concrete breaker, using a motor, gears, and springs. The 3 of them were discarded for their complexity and high cost. Another 3 designs were created to automate the process of breaking concrete. The power hammer design was a great concept that the sponsor liked because it offers a hands-free operation that requires a little to no user input. The 3 of them use a motor to cycle the process, and they were all discarded because of the high cost of the motor and the complexity to manufacture the parts and assemble them all together. A sliding hammer was one of the concepts that caught our sponsor's attention. It uses a hammer that slides into a guided shaft with weights that can be added to the top of the hammer to increase the impact energy when hitting a chisel in the bottom. Folding support legs ensure portability and total modularity. This design was complex to make, but it helped us shape the final design. Another tripod-shaped design was made using a brake winch that is sitting on the top of the tripod, which will be used to lift the weight that will be dropped down on a chisel. To release the lock of the winch, an actuator was going to be used to release the lock and let the weight drop. This design was again discarded for its complexity and cost of parts. Since each one of the team members created multiple designs, we had to use a concept scoring matrix that helped us decide on the final design. First matrix was used to narrow down the big number of designs we had. Then, another matrix was used to choose the final design. We created these matrices using the older customer requirements before they were changed by our sponsor. This is the design that was chosen using the matrices we created with the older customer requirements. It ranked the highest for its ease of use, simplicity, and for the parts used that can be found easily. It works by lifting a sledgehammer up to a certain angle that will be dropped on a chisel, and the cycle would repeat using a motor and springs. This design was discarded later after the sponsor chose not to have the machine automated for the high cost of the parts used. During the designing process of our final design, a failure modes and effects analysis was created to have a bigger understanding of our design and figure out all the factors that will result into some of the main failures, and to have a plan to attack these factors to prevent any safety issues. The analysis showed that the biggest failures are not being able to break the concrete, release of the rope will not go smoothly, failure of the hinges, and the hazards of the operation during the release of the handle. This is our final design that meets all the requirements that were given to us by our sponsor. It will be discussed later in the video by Michael Eliassi.
The device can be divided into 4 major sub-assemblies. Each have their functions and drawbacks, but work together to achieve all the customer requirements. There are 4 major sub-assemblies that the team laid their focus on. Subsystem 1, or the base, that will hold all the weight of the system. Next is Subsystem 2, our most important sub-assembly, since it deals with the interaction between hammer and concrete. Subsystem 3 is the cantilever beam that holds the hammer. Subsystem 4 is the hinge, which was added to improve portability of the design. We will dive deeper into these to show where they are located and define their functions. Subsystem 1 takes a closer look to the stability and friction of the base, and therefore the whole assembly. This subassembly is made up of scheduled pipes to balance the strength and the cost. Other than carrying the weight of all the components in our system, the base needs to be stable. Since our design is 10 feet tall, it is more likely to tip over while operating. Therefore, a base angle is added in the design. This angle prevents the whole assembly from tipping over when the user will be operating it. Another key function is to prevent the design from slipping. Therefore, a rubber padding will be added to the design to increase the friction between the concrete and the base. Let's talk about our team's most important subsystem. This essentially will focus heavily on the impact between the hammer and the concrete. This is one of the most important subsystems because it fulfills one major objective, that is, to break concrete. Therefore, our team spent a significant amount of time to assess if this device is capable of breaking concrete or not. Since it was our topmost priority, our team conducted complicated finite element analysis to determine if the device was capable of delivering its primary objective. Its function was to break the concrete and have a uniform contact surface area to prevent any discrepancies between the runs. To best fit the project budget and shape requirements, a boat anchor such as the one shown here was used for physical testing. This subsystem mates with the cantilever beam and the pulley assembly. This is another important subassembly that needs to work perfectly since it will do most of the heavy lifting while hosting one of the most dynamic systems of this design. The cantilever beam's function is that it needs to be sturdy enough to be able to lift 35 pounds and keep it at least a foot away from the central hole. Major concern with this system is that it is susceptible to fatigue and eventually the screws may shear through the wood over time. As can be seen in the picture, it mates right at the top of the design and hosts a pulley which aids the hammer to move in a linear motion. A hinge was added in the later phase of the design process to fulfill customers' portability request. Its function is to provide portability and sturdiness when the design is upright. As it can be seen in the pictures, it mates right at the center and helps in converting the 10 feet tall design into a 5 feet portable design.
Here is the final prototype that was approved for production. I will go over how the previously mentioned subsystems work within the main assembly. Our folding mechanism relies on a simple 3.5 inch door hinge along with the clamp style latch. Once the latch is released, the top 5 foot post folds in half for storage. Here's another view of the same operation. The next subsystem is the cantilever beam used for distancing the weight away from the assembly. 1-inch screws hold several pieces of 2x4 together. Calculated loads for these screws are 3000 psi for shearing, and the weakest link being the pull-out force of these screws, which we have calculated to be slightly over 100 pounds per screw. 2 simple roller wheels are encompassed in the cantilever assembly, and simple rods allow the cable to roll freely over the top of the structure. The base uses a series of Schedule 80 half-inch pipe connections. An 18-inch pipe connects to the flange, which then extends out to a T-connector, where an 18-inch pipe on the front side connects, followed by the 36-inch pipe in the back, with a 6-inch leg to keep the whole assembly from rocking backwards during operation. A small pulley at the bottom routes the cable to allow for the final path of operation, where the user pulls the cable and releases the weight. We will now demonstrate the principles of operation of the H-style concrete breaker. A simple handle is connected to a cable where the customer then proceeds to pull backwards and releases from a safe distance. The calculated impact force is calculated as reaching 5,500 psi, which is about 1,000 psi over the threshold needed to fracture a 4-inch slab of concrete. The bill of materials generated shows the minimum cost of production for this device is about $155, with the final weight coming in at an estimated 107 pounds. Due to the ongoing pandemic, we were unable to build a physical prototype. However, we still wanted to validate our concepts and ideas. To do this, we purchased a 35-pound anchor and went to find a concrete slab of 4 inches approximately and proceeded to drop it from heights of 10 feet to see what would happen. Here is some media from the event.
That's pretty good.
Nice.
It is breaking it. It's chipping it.
It's just chipping the surface.
That's good. Maybe it's something.
We began to notice that the concrete pad was absorbing the shock of the dropped hammer,
so we decided to go to the edge of the pad where we believed it would fracture more easily with repeated drops.
3, 2, 1. Ooh, right on the crack.
Right on the crack.
Nice. About 6.
In order to gauge the braking force of the concrete, we found some nearby bricks, and using a 12-pound sledgehammer, we calibrated our strengths and abilities.
Our design meets the customer's key requirements in every way. The portability of the breaker is achieved through the hinge that enables the design to fold up while using standard materials found in most local hardware stores, keeps costs low and assembly time quick for the customer. The pulley system works to keep the operator safe, as they will not be exposed to potentially dangerous whole body vibrations. But most importantly, this concrete breaker breaks concrete. Using finite element analysis to assess the impact of the hammer on the concrete, we can confirm that the dropped hammer exceeds the tensile strength of concrete, thus breaking it. This data was furthermore supported from physical tests in which an anchor, similar in size and weight to our design, was dropped from 10 feet onto a concrete deck.
In the conclusion, the final design of the concrete breaker met the customer requirement, where $153 is the budget of the design, and this cost is around the customer requirement. Vibration is causing exposure to the whole body, and the final design that was created does not require a vibration to break the concrete to make it safe to use. 30-pound weight drops from 10 feet can break 4 inches of concrete. The new design of the concrete breaker weighted about 60 pounds, and the leg of the concrete breaker can be twisted to make it easy to move. A pulley system was made which make it easy to lift 30-pound weight. Thus, the final design of the concrete breaker that the group members created will allow people to buy because it's cheaper than the old design, and they can use it without any help from a specialist because it's safe and easy to use.
The next steps for our team are to build a full-size physical prototype. Once the prototype is built, we will make a pitch to onboard investors. With more money, we will redesign our breaker to include automatic functionality, an optimized chisel suitable for larger production budget, and a motor to increase the impact capabilities of the breaker. These enhancements will make operation even more comfortable to a host of users and more damaging to stronger types of concrete. This Capstone project has been a great learning experience for our team, but the number one thing we're all taking away from this can be summed up in a short cliche. Keep it simple. We had great intentions and expectations starting out, but realized 3 months in, the path we set for ourselves was too complicated. We solved this by taking a step back and simplifying our design. Even though that meant completely starting over in our case, it was clear then that simpler was indeed better.